Okay, so the first chapter that we're going to look at is chapter two, measurements. Specifically, let's take a look at 2.1 significant figures. Whenever you're making a measurement or whenever you're doing a calculation, there's always some point where you have to say, okay, I'm going to stop here. This is the number I'm writing is no longer significant, right? When you're writing something down in a lab, for example, you might write 21.6430021, and you're just going to keep going. And some people write all those out, and they shouldn't. They have to decide, hey, when is this no longer relevant? There's a certain point where the numbers are no longer significant. My example is, let's say that I'm driving, commuting a long way to go to school. And so I travel 70 miles to get to school. Once I get there, I park and I walk into the classroom and I travel another 300 feet. So how far have I traveled to get to class? Well, I've traveled 70 miles. That 300 feet I've gone to get to class is irrelevant compared to the measurement I took to get there. So the 300 feet is insignificant. The 70 miles is significant, right? So there's a certain point we have to say that's no longer true. So whenever we're taking a measured number, we are going to figure out what the significant figures are by this kind of idea here. So first of all, a number is significant, okay? It is significant if it is not a zero. So if I were to write down a measured number, and it's really important this measured number, 231.16. Every single digit there is considered significant. So I have a total of five significant figures there. From the beginning, by the way, I'm going to start on the left and I'm going to work my way right. So from left to right. But really what we're going to do is the first significant figure I run into is the first non-zero. So that's the first significant figure. Okay. So that one and everything after it counts because they're all non-zeros. All right. So let's try the zeros that are in between numbers. So if I have 20.02, again, that's the first significant figure because it's the first non-zero. That and everything after it is going to be considered significant. There are, that's right, four digits there. Two significant, zero, zero, and two. All of those are considered significant figures. So all significant, all significant. All right, the zero at the end of a decimal number. So if I were to write some number like 2.200, right? Again, the same idea, find that first significant figure, that one and everything after it, all of those are considered significant. Why are those zeros there if they're not important, right? I would just, if those zeros were not important, I would just write 2.2. And you have to watch out because your calculator is not going to add those zeros. You have to make that decision. So if I write 2.200, I'm writing those because they mean something. So adding those zeros behind there means that they are relevant. They're supposed to be there. If I didn't need them, I would just write 2.2, and I didn't. I wrote the zeros. And then finally, any digit in a coefficient number written in scientific notation. When we do scientific notation, 1.31 times 10 to the negative 4, we ignore everything other than the coefficient. All of the numbers here are going to be considered significant. Doesn't matter if it's zero, doesn't matter how it's written. There are three significant figures there. Okay. A zero is not significant. The only time it's not significant is when it's a place holding zero. So let's do a decimal, 0.00310. Again, the way that we should start to think about it is work from left to right and first find my first non-zero. This right here is my first non-zero, right? So that's the first, and we're going to consider that, and that's always how we do it, right? From left to right, find the first non-zero. That is considered significant, that and everything after it. There are three significant figures in this one. And then zeros at the end of a large number. And so this one is the one that confuses people a little bit, and we're going to look at it in two different ways. Um, and then I'm going to kind of summarize it in a little aside here. But so if I were to do 21 comma 00, 21,000, okay? Actually, yeah, 21,000, that'll work. Again, do the same exact thing. Let's find the first non-zero, which is going to be that 2. Well, it turns out when there is no decimal, right, we are going to find the last significant figure, which is that 1. Only those two are considered significant. These zeros right here, all they're doing is holding the place. All they're saying is that 21 is 21,000, right? Without those zeros, I still need to represent 21,000 somehow. I can't just write 21 because those are two different, right? If you were supposed to get $21,000 and you got $21, you would be upset. So those zeros are significant in terms of putting the position of that 21. So 21,000 is putting that in position. So this one says, okay, and this measured number has two significant figures. And there's a little bit of a thing to worry about or thing to look for here. So if I have 21,000 and I put the decimal here, how many sig figs do I have? Well, as soon as I see that decimal, that and the first sig fig and everything after it is considered significant. This one has 5 sig figs. So really what we're doing is we're looking for a decimal. So let me simplify this even more, not worrying about all these different types of ways of looking at significant figures. I'm going to simplify it just a little bit before we go into that example. So the simplification, the simplified version of it is this. 1, find the first non-zero. Okay, so we're going to do it. I'll do an example. I'll do an example over here to the left. So let me do 21,450. And then I'm going to do 0.02100. Okay, so find the first non-zero. I'm actually going to do these in the reverse order, actually. Up above. So we're going to find the first non-zero. That's my first non-zero. That's my first non-zero in that number. We can do both of these together. Okay, so the second question is there a decimal? If there is a decimal, it's all significant after first. So the very first one is there is a decimal present, so all of those are considered significant. This thing has 4 sig figs. Okay. If there is no decimal present, find last sig fig. Oop. Find last non-zero. And in between those is going to be significant. So in this number, that is the last non-zero because there is no decimal. So I'm just going to do between those two. This one also happens to have, just randomly, happens to have 4 sig figs as well. If a decimal is, so basically, if a decimal is present, find the first one, that, and everything after it. That's the rule. Most things are going to have a decimal. If there is no decimal, find the first and find the last non-zero, them, and everything in between. Okay. So with that said, how many significant figures do we have in these numbers here? So we're going to do this in class. So give this a go. How many sig figs do we have in this number here? These numbers here. Okay. So we have two different types of numbers. We've talked about significant figures, and I've mentioned how important these things are just in terms of saying, hey, there are certain things that are important. Well, we actually have two different types of numbers. An exact number. An exact number is counting. So anything you count is an exact number. What I mean by that is if you count the number of people in the room with myself right now, it's just me. There's one person in the room. No one's going to argue that. No one's going to say, oh, you've got 3 people in the room. No, there's no there is no worry about me being off or uncertain about that number. There's one person in the room, right? When we're in the classroom, I can count every single person in the class. You can as well. We can say that's the total number of people. Those are exact numbers. So counting is exact. They are not driven by sig figs. Sig figs are not important there. Conversion factors. There are 3 feet uh, in a yard, right? Or there are 12 inches in a foot. Those things are those are accepted. Those are accepted values that no one's arguing with that. There's no like uncertainty there. There's exactly 12 inches in a foot, and that's an exact number. So it's not driven by, we don't have to worry about significant figures. Measured numbers are different. Measured numbers, there is some amount of variation. So if I asked you to read this coin length, so you look at this coin and let's talk about what is certain and what is uncertain based on the measurement. So all of these are going to be based, all of our measurements, all of our uncertainty is based on what we are measuring with. What I mean by that is I'm going to say 2 in the ones place. This I am totally certain of. And everybody should be certain of this. If I said, hey, this is 1 centimeter, you'd be like, no, it's absolutely not. It's between the 2 and the 3. So I am absolutely certain of the 2, okay, in the ones place. The next one is where the uncertainty comes in because these hashes right here allow me to be certain. So this is accurate out to one more place because I am certain of the 2. I'm going to guess it's about halfway. So that is, I'm uncertain about that because if I said 2.4, you'd be like, okay, yeah, I could see that. Or 2.6, you're like, oh yeah, I could probably see that. So there is a certain amount of buffer in there. So I say 2.4, you may say 2.4, may say 2.6, but all of those are accepted values because of that tool used to measure it. We are certain of the 2. We are uncertain of the one beyond. So you take the smallest hash and you have to guess one more. So this is accurate out to the 10th place because of the thing that we're using to measure it with. Okay. So the length of this coin would be 2.5 centimeters. By the way, we're going to talk about uncertainty in a second, plus or minus 0.1, right? There is a little buffer. So how do you measure this? Okay, so this is a graduated cylinder. A couple of things. This is called a meniscus right here, this little shape. This little curve is the meniscus. We are going to read at the bottom of the meniscus. All of our readings are done at the bottom of the meniscus. So we're always going to read it at the very bottom, okay? If we take a look at this measurement, what we notice is it's above 20. So let's read this. So we should all agree that I'm going to have a 20 at 2 in the tens place because it's above 20, it's below 30. Each of these little hashes, so this is 5, 6, 7, 8, 9. So each of these is 1. So that means this is 20. Let's see. So this is 20, 21, 22. So it's above 21 but below 22. So I'm going to put a 1 in the ones place. So 21 point, I don't have any measurements here, but I can't say 21 because it's a little bit above 21. So this is where our guess comes into play. I am certain about the 2. I am certain about the 1. And now I'm certain about the 20, I should say. I'm certain about the 1. And now I have to guess. It looks like maybe about a little more than halfway. So 21.6. 21.6. If you said 21.5, we'd be like, okay, sure. 21.7, yeah, sure, okay. But if I said 21.4 or 21.8, you'd be less certain. So what we notice is there is some amount of uncertainty. You're just not quite like, okay, I can see it, or you can't see it. There's some amount of uncertainty in that last number. So if you're positive about a number, that's not the uncertain number. You got to keep measuring further out. So this one is measured in milliliters. Always have to add the unit. So there we go. That's how we read. It's the bottom of the meniscus. It's often difficult in the lab. You always put something behind it. That usually helps. So with that said, let's read these. We're going to do this in class, and we're going to discuss the uncertainty with them. Okay, that brings us to uncertainty. The uncertainty is basically, look, uh, there is some small uncertainty, and I don't want to reuse the word uncertainty here, but there is some small deviation from the recorded value, or recorded value depends on who is reads the measurement. So in that coin, I said, hey, I would be okay with 2.4, 2.6. So we have this kind of assumed range of, look, there's a little bit of uncertainty here. So anywhere in this range would be just fine. So in this measurement here, I said I would call this 2.5. I'm going to say plus or minus zero point 0.1 centimeters. So there is a small little buffer. You're okay with 2.56, you're okay with 2.54. This plus or minus kind of takes care of it. We're not really going to worry about this too much in this class, but just know that there is always that little bit of uncertainty. So with that said, and how many, what do you measure this other coin as with this new ruler? Because the ruler is more accurate. So where do you measure that? So I'm going to blow it up a little bit, but we're going to take a look at this in class. Okay. How about this one? Measure this one with the uncertainty. We're going to talk about this in class as well. Okay. So significant figures and calculations. So let's talk about this coin again. It keeps coming up. We have to keep in mind that we are only as accurate as our least accurate measurement. So when we are doing measurements, we have to make sure we keep track of significant figures. So we said that this was the diameter of this coin is 2.5 centimeters. Okay, so 2.5 centimeters is the diameter of this coin. Okay, so what's the radius of the coin? Well, the diameter um, is equal to 2.5. But if I take the radius, I want to take the diameter and I want to divide it by 2. Okay, we can do that. So my diameter of 2.5 centimeters divided by 2 gives me 1.25 centimeters. Okay, great. There's my radius, right? That is the correct answer. Not quite. Okay, so with that, let's just back up. If I look at this diameter measurement, there's the first one. I'm going to highlight the whole thing. There are two significant figures here. Okay. So then we divide it by 2, just to measure it, just dividing it by 2, and we end up with this radius. There are 3 sig figs. The problem with this is we went from 2 sig figs to 3 sig. How did we improve? How did we end up with a number in the tenths place by just dividing it by 2? The answer is we shouldn't have. So if I start with 2 sig figs, I have to end with 2 sig figs. Okay. So what that means is I am going to underline the second sig fig, and this is important when we're rounding. I'm going to underline this second sig fig. So how do we round that? So the radius of this is equal to 1.3 centimeters. 1.3 centimeters is the correct measurement here because if I start with 2 sig figs, I must end with 2 sig figs, which I have. Okay, so that is taking a look at the first part of significant figures in a calculation. So significant figures in a calculation, we have a set of rules that control sig figs in a calculation. And these rules are relatively straightforward. So let's take a look at the first one. So we're going to look at this in two ways. If I'm going to be adding or subtracting, I've got one set of rules. So add or subtract, I am going to go with the fewest decimal places. That's a little bit of a misnomer. Fewest decimal places, really it's going to be the highest place. And what I mean by that, and we'll take a look at an example of this. So if I were to take a number like 1.34 plus 1.1, okay? So if I'm adding, and so if I add these together, just plug this into our calculator, we're going to end up with 2.44. So there's my final answer, okay? But what I'm really interested in saying is, okay, how many decimal places, or really what's the highest place? So I'm going to look at just this one, the last place I see a significant figure, okay? And that one is in the hundredths place, okay? This is the last significant figure I see. This is in the tenths place. Or if you have a decimal, it's much easier. This one has two decimals. This has one decimal. Okay, so the one that's least accurate is this measurement right here. So that means I'm going to limit my answer to the same number of decimal places that has, or the tenths place. So I'm going to limit it to that. I'm always going to underline where I'm going to round. So we're going to call this 2.4. There's my final answer. My final answer is always going to be the least number of places, okay, or the least number of decimal places. So 2.4 is where I'd round. We always get used to underlining. The other way that you can kind of look at it, this is another way of doing it. So if I had 1.34 plus 1.1, okay, we can set it up like you would a problem. I'll move it over here. And what you can simply do is you can cut it off. Let's say I'm going to put the numbers down and then I'm going to do the rounding. So 2.44, and then I'm going to take this line and I'm going to say, okay, this is the last sig fig here. I'm just going to draw a line in and we're just going to cut it off there. Actually, I'm not going to do that. I'm going to say I'm going to round here. So either whatever you're comfortable with, if you want to like line them up versus if you want to say, okay, this is how many it needs to be rounded to, either of those will work. The reason that we kind of use that second option is if I am adding together some numbers like 23,100 plus uh, 650. Okay. So right there, saying we don't have any decimals for these, so we have to decide where to round for this one. So I'm going to add these two things together. So 23,750. And again, I'm going to look at the lowest place. That's the tens, and this is the hundreds. That means I am going to round my answer to the hundreds place because that's the higher of the places. So this would round to 23,800. There we go. Done. Okay. Again, we could use this other method by saying, all right, I've got 23,100 and I've got 650. I'm going to add them together to get 23,750. And then I'm going to take that line and put it in where I see the last significant figure. Oh, sorry, the last significant figure. See, I haven't screwed that up. It's right there because we have to look at the highest. That's where I'm going to round. Same idea, but a different way of looking at it. It's up to you to decide how you want to do it. Then we have the easier version of it, was multiplication and division. So when you have multiplication or division, life is much simpler here. Um, we just look at the number of sig figs. So if I'm taking 3.12 times 2.61043. So a lot of things here. I've got to do the quick math. But the idea being that you can use, you're going to simply plug this into your calculator and don't worry about rounding right away. I'm going to take all of these numbers. So 3.12 times 2.61043. I'm going to plug that into my calculator and this is what I get. 8.1445416. All of those numbers, you write them all out. And then you decide, okay, this one has 3 sig figs. This one has 2, 4, 6 sig figs. So I'm going to use 3 sig figs. 1, 2, 3. There's my third sig fig. I'm going to underline it. That is where I'm going to round. My answer is 8.14. Boom. That's it. If you're dividing, it's the same thing. One with the least number of sig figs, your answer should match the least number of sig figs in the measurement. That's it. Okay, so with that said, there are a bunch of problems here. I think I provided you the math for these, but we're going to walk through these in class. And then the next section is going to be on significant figures and calculations. All right.